Imagine somewhere in our universe an utterly strange world, a place where time could both speed up and slow down, from where we could journey into the past and the future. Somewhere time could even split in two. Incredibly, this is no alien world. It's our world, and it's all around us. Now, for the first time, science is enabling us to see what for thousands of years has remained hidden: the true nature of time. We live in a world governed by time. From the tiniest of cells to the most distant of stars, our entire universe is subject to the beat of a constant clock. And because time is everywhere, we think we know it. We know that it's regular and it moves in one direction. We know that it's universal and eternal. And we know that it never, ever stands still. But how can we be so sure? How much of what we think we know about time is really true? In this program, I want to get to the bottom of what time really is. And in doing so, I'll be challenging some of our most cherished beliefs. As a theoretical physicist, it's this hidden time that has always fascinated me throughout most of my professional career. I'm going to explore the very limits of our universe in order to uncover just what time really is. And in the process, I'll be revealing an astonishing secret, nothing less than our ultimate destiny, the future of the universe, and the fate of time itself. Of all our assumptions about time, one of the most obvious is that time is regular. That a minute will always be a minute. For everyone, everywhere. Here in the Swiss Alps, I'm searching for something that challenges this assumption. Something that, if time was as regular as we think it is, shouldn't exist at all. Well, I'm now 11,000 feet above sea level, and I'm out of breath, and actually feeling a little bit dizzy. Now, the bad news is, I still have a ways to go to reach the top of the Alps, because what I'm looking for is something that becomes more plentiful the higher you go. And this is what I've come to see. It's a particle counter, telling me that the air around me is full of tiny particles called muons that come from all the way out there. Muons are short-lived particles formed when cosmic rays from space collide with the upper atmosphere. But the big mystery is how they come to be down here on Earth. Because, with a lifespan of just 2/millionths of a second, muons should only live long enough to travel a few hundred meters. And yet, here they are, after a journey of several miles, something that shouldn't be possible. So what exactly is going on? The answer to this mystery, the reason why muons can reach us at all, is so extraordinary that from the moment it was first proposed, it literally rewrote the rule book of time. Less than 100 miles from the Alps lies the affluent city of Bern. In the early 1900s, this was home to a young German physicist who would change the way we looked at time forever. His name was Albert Einstein, and he's been my hero for the past 50 years. Shortly after arriving in Bern, Einstein was offered a job. This building was once the Office of Intellectual Property. It was here that Einstein spent 7 years as a patent clerk, assessing the technical merits of inventions ranging from refrigerators to radios. One technology in particular had a huge impact on the young Einstein. Between 1901 and 1904, the number of patent applications for electrical clock devices almost doubled. And that's because time was fast becoming the issue of the day. This is the famous clock tower, which has stood in the middle of Bern for the past 200 years. Einstein must have walked past this clock every day on his way to work. But back then, clocks were so inaccurate that this one and one in Zurich, a mere 75 miles away, would have differed as much as 4 minutes. With the growth of Europe's railways, such time discrepancies were becoming not just inconvenient, but also dangerous. Borne out by a steep rise in the number of serious train crashes. All of a sudden, time was on everyone's lips. But for Einstein, this new world of trains and clocks was more than just a talking point. It was an inspiration. In 1905, in this, his first-floor apartment, Albert Einstein put the finishing touches to his radical new theory: special relativity. One of 5 papers published by Einstein in 1905, special relativity would make us think about time in a completely new way. Einstein's astonishing claim was that time was not regular at all. It could beat at different rates. Time changes, depending on relative speed. Imagine for a minute that my tram is capable of traveling at phenomenal speed, just a fraction less than the speed of light. According to special relativity, the rate at which time flowed on this speeding tram would depend on whether you were on board or looking in from the outside. So while for me, it would seem as though time was passing perfectly normally, For me, sitting on the pavement, assuming I could somehow peer inside the tram, time would assume a totally different quality. Looking in from the outside, I'd sense that time on board the tram was passing much more slowly. That's because, according to Einstein, the faster an object moves, the slower its time will run to someone observing from the sidelines. In other words, time can vary. It's all a matter of speed. And that explains the mystery of how our muons reach the Earth. Because muons travel near the speed of light, relative to the Earth, their clocks have slowed down. So much so that they exist long enough to reach the Earth and be detected. Time for our muons has stretched. It beats very differently to the way it does for us. For hundreds of years, time had been seen as fixed and immutable. None other than the grandfather of modern science, Sir Isaac Newton, had pronounced that time exists in and of itself, without reference to anything external. But we now know that time isn't set at a fixed rate. Time is not absolute. Now, the effects of special relativity are so small that they have no impact on our daily lives. But the fact that they are there at all has changed everything. Because if time is relative, if time is flexible, then our belief in the immutability of time is wrong. And if we can be wrong about something as basic and as fundamental as this, then in what other ways might we be mistaken? Time has intrigued humanity throughout history. More than 1,500 years ago, a former heretic turned Christian bishop wrote a treatise on time that's as provocative today as when it was first written.
What we have here is the first English translation of Augustine's Confessions. Augustine was a 4th century philosopher and theologian, and the Confessions is his autobiography. But besides relating incidents in his life, it also contains some fascinating reflections on the nature of time. And he starts with a very commonplace reflection, that time consists of time past, time present, and time future. But, says Augustine, the future does not yet exist, the past no longer exists, and the present takes up no time at all. So how then can time exist?
Over 1,500 years later, the mysteries of time continue to preoccupy philosophers. But there's one thing most of them are in agreement about.
Time is very paradoxical. It involves notions of eternity, of infinity, of beginnings and endings. All these are extremely difficult notions to grasp. But that doesn't mean to say that we have to banish temporal order. It seems to me that we can still make sense of time as being an ordered dimension of events.
Even philosophers accept that time is predictable and ordered, that things can only be in one place at one time.
Did either of you play cards?
I play a little poker.
You play poker? Yeah. So you can shuffle cards, can you?
Oh, no.
No?
I let someone else
So
shuffle.
do you shuffle like this?
Yeah.
Yeah? That's called the overhand shuffle.
Okay.
Because if you don't shuffle cards that well, you can try this one. This one's pretty good. It makes a complete mess of the deck of cards. Some cards go back to face, and some of them are like back to back.
Our complete trust in temporal order is the reason why we delight in the obvious impossibility of magic tricks.
Go back to face and face to back. As I said, it makes a total mess. I'll just show you. Some of the cards, they're like face to back. Not very good for playing poker or blackjack. If you press the button here, press the button, boom, snap your fingers, they all come out the right way, which is rather handy.
That's
Pretty cool, isn't it?
Pretty good.
Wow. My job as a magician is to manipulate people's faith. Hi, how you doing? Can we stop you for a moment? People realise that things can't disappear and reappear. I'm going to run through the cards and you say stop wherever you like. If you do your job properly, you can make it look as though two things can be in the same place at the same time. And to that end, essentially, you can make it look as though you're manipulating space and time. Have you ever seen magicians use these before?
Yeah, I've seen them.
I'll show you a trick with two of them.
On you.
Okay, so can you hold your hand out for me?
Sure.
A classic way of demonstrating the manipulation of space and time can be done using the sponge ball trick. It's 100 years old, but it's great. But essentially, you take a ball in your own hand, and the spectator holds a ball, and you can do it in such a way that you can look as though you can manipulate space of time, and it looks as though the ball has disappeared from your hand. So when the spectator opens their hand, suddenly they have two. That ball has vanished from your hand and it's reappeared in theirs.
But believe it or not, this sort of behavior isn't always an illusion. Beneath the surface of our common sense world lies another world, where magical things really do happen, where the impossible can be made real, and where time can perform the most incredible tricks. That place is inside the atom. For years, scientists had assumed that in our universe there was nothing smaller than an atom. The very word atom, in fact, comes from the Greek word for indivisible. Then in 1897, an Englishman named J.J. Thomson made an astounding discovery, that inside the atom there were even smaller particles called electrons. Thomson's discovery opened the door to the amazing world inside the atom, a world where everything, including time, behaves in a truly alien fashion. Physicist Ian Walmsley has been studying this microscopic world for almost 30 years.
When we get inside the atom to this world of subatomic particles, the ideas that we have about the way the world works completely have to change. We can't think in the same sorts of common sense terms that we think of in everyday experience.
In fact, this subatomic universe is so strange that time becomes chaotic. A startling discovery that emerged from the study of light. Light consists of individual particles called photons, known for their wave-like properties.
Waves have a very interesting sort of phenomenon. It's called interference. When two waves come together, they can add together and reinforce one another, or they can cancel one another out. And this interference is a ubiquitous property of all waves, not just water waves, but also light waves.
But in the early 1900s, scientists noticed something very odd about these light waves, something that proves that time isn't always ordered. In this reworking of a classic experiment, once described as the most beautiful in physics, single photons, or particles of light, are fired down a darkened tube towards a camera, one at a time.
So we have here a very simple apparatus. It consists of a light bulb at this end and a camera at the other end that can register the light. And in between, the light encounters a pair of slits etched onto this piece of glass, through which the photons can pass on their way from the source to the camera.
The purpose of the experiment is to study the behavior of photons as they travel from one end of the tube to the other. To begin with, the individual photons are sent through just one of the slits.
Each of these dots arriving represents a single photon So most of them are coming along this point. Some of them lie above or below that point, but the distribution is nice and smooth.
Now the second slit is opened up, and the experiment repeated. Each single photon must still pass through one of the two slits, so the results should still be the same.
Classical logic would say that what we would get when we open both slits is just the sum of these two detection patterns.
But what we actually find is this: an interference pattern, something that should be impossible.
What that implies is that the single photon is somehow going through both slits at the same time. It's not making a choice as to go through one or the other, but is going through both simultaneously.
In other words, each photon exists not just in two places, but also in two times.
So we have this very strange notion that this single photon can be in two different places at once. It could be delocalized. But we can think also of a single photon being in two different times. So both space and time have become delocalized and fragmented.
On the surface, we feel time is ordered, but that belies a different reality. We are totally unaware of the chaos and unpredictability that lies deep within the atom. Not surprisingly, our understanding of time comes from our everyday experience. And it's for this reason that we cling to yet another of our assumptions about time, that it never stands still. In fact, one thing that sets us apart as humans is the knowledge that time waits for no man. That time doesn't merely exist, but is constantly flowing. But one discovery proved that this isn't always the case.
Dr. Tom Bolton of the University of Toronto made more than 40 observations of Cygnus X1.
In 1971, astronomer Tom Bolton embarked on a project to observe a mysterious X-ray source called Cygnus X1, an object assumed to be a distant neutron star.
I started to look at Cygnus X1 because I thought it would be a good opportunity to determine the mass of a neutron star. And nobody had done that yet.
Cygnus X1, some 8,000 light-years away, is one half of what's called a binary system.
The binary system is a pair of stars that are gravitationally bound to each other, just like the Earth is bound to the Sun, and they orbit about their mutual center of mass.
By measuring the speed and orbit of X1's binary partner, Tom was able to work out the mass of his neutron star. But the figure he arrived at was far, far bigger than the one he'd been expecting.
That turned out to be about 10 solar masses, with a significant error, but still way too big to be a neutron star. So I had to start thinking about what are the alternatives if it's not a neutron star.
There was only one possibility that fitted the data, but it was something that few people believed actually existed.
As far as I knew, the only object that would fit that description and produce X-rays was a black hole. So I said so.
Tom's discovery caused a sensation. The first incontrovertible proof that, far from being a figment of people's imagination, black holes were in fact very real indeed. Since their discovery 25 years ago, we now know that the universe is teeming with them. But it's how black holes affect time that make them so unusual. Black holes are so massive that their gravitational pull approaches infinity. And according to Einstein's second theory, that of general relativity, very intense gravity slows time in a similar way to moving at very high speed. So if you were to watch someone fall into a black hole, you'd notice that their time was beginning to slow down. So much so that at the very center, where the gravitational pull is infinite, time would stop altogether. Time would cease to exist. That there are places where time can come to a grinding halt seems frankly incredible. But that's only because we live in such a uniform corner of the galaxy. Warmed by a benevolent sun, far from any extremes of gravity. Beyond our everyday environment, time is very different. Not only is it irregular, it's also chaotic. It can even stand still. But for all its vagaries, there's one thing that time never seems to do, and that's turn back on itself. Although time may be hard to define, there's one truth that has always been beyond doubt, and that is time only has one direction, and that is forwards. Which, when you think about it, is a little odd. After all, my physical environment offers me enormous freedom. In my three-dimensional world, I can go any place I choose. But with time, my freedom to move about is confined to one direction. Of course, in our imagination, it's a completely different story. In 1895, a short novel by a former schoolteacher named H.G. Wells brought to life one of humanity's oldest dreams.
So I travelled, stopping ever and again, in great strides of 1,000 years or more, drawn on by the mystery of the Earth's fate, watching with a strange fascination the sun grow larger and duller in the westward sky, and the life of the old Earth ebb away.
In the earlier part of the 19th century, there were stories that involved time travel or kind of visions of often the future. But what tended to be different was these were often kind of explained in terms of sort of either dreams or supernatural occurrences or visions or something like that.
Wells' story, called The Time Machine, took the idea of time travel and made it seem scientifically viable.
I'm afraid I cannot convey the peculiar sensations of time travelling. They are excessively unpleasant. There's a feeling exactly like that one has upon a switchback, of a helpless, headlong motion.
When he's describing the physical sensations of time travel, Wells talks about a nightmare sensation and excessively unpleasant and so on. And he, you know, the sort of the staccato sort of flashing by of day and night as being incredibly sort of nauseating and disorienting. It's very, very powerful for the reader because it does make you believe that you're in a kind of real flesh and blood body. And again, it's this intersection of the physics of time travel and the philosophy of time travel with the biology of a real person.
The Time Machine was an enormous success, offering people a glimpse of what it would be like to make the ultimate escape. The escape from time, even from death.
questions of time are obviously incredibly important to us all in our everyday life, and questions of mortality. And mortality is obviously the kind of the horizon of time for each of us individually. And I think that anything that allows us to sort of have a sense of sort of escaping that kind of inevitable end of our own time is quite appealing.
But now, after years of being treated as science fiction, it seems that time travel could be science fact. The thing is, the laws of physics don't have any problems with time running backwards. So we physicists believe that it just might be possible to build a time machine. The only obstacle we face is one of engineering. That's because the theoretical blueprint for our time machine already exists. A machine that's secret lies deep within our microscopic universe. At the tiniest subatomic level, the fabric of space and time becomes so unstable that it starts to behave like a foam, its surface alive with tiny bubbles momentarily popping in and out of existence. We call this quantum state the space-time foam. It's thought that contained within this foam are objects called wormholes, tiny passageways between 2 points in space and time. The secret to building a time machine is to stabilize the space-time foam long enough to make one of these wormholes permanent. And the way we do that is by subjecting it to enormous amounts of energy. I'm standing 100 meters above what will be, when it's finished, the world's most powerful particle accelerator. This machine, scientists hope, will help to unlock some of the secrets of the mysterious world of subatomic particles, the building blocks of our universe. This tunnel is 27 kilometers in circumference, and it houses the accelerator. Inside this chamber, 2 beams of subatomic particles will be traveling in opposite directions, boosted to near the speed of light. As the protons within the beams collide, they shatter into even smaller particles, releasing bursts of energy roughly 500,000 times greater than those inside a nuclear explosion. But even the most powerful accelerator on this planet can't produce enough energy to stabilize a space-time foam. To do that, our particles would have to be moving even faster, and that would require an accelerator of truly enormous proportions. By adding even more energy, blasting the plasma with lasers, we can finally stabilize space-time foam, long enough to pluck out a minuscule wormhole. The next task is to enlarge it, and even that is scientifically possible. In 1948, a Dutch physicist named Hendrik Casimir introduced us to a mysterious new force called negative energy, complete with anti-gravitational properties. So far, we can only create minute quantities of this in the laboratory. But one day, if we can create enough negative energy, we might be able to increase the size of a wormhole. And this is how we think our wormhole would look. Each end a sphere, held in place by an electric field, invisibly connecting 2 points in space and time. By subjecting one end of the wormhole to a huge gravitational field, we could bring its clock almost to a stop. This turns our wormhole into a time machine. Both ends existing in the same place, but at different times. Our ability to build such a machine is still some way off. But just knowing that time travel is possible is enough to turn yet another of our assumptions on its head. Time isn't necessarily one way. It can move back as well as forwards. Within the fabric of our universe lie the means to a temporal freedom that until now has only existed within our imagination. So what would we make of the chance to cruise through space and time? To visit the past, perhaps even to change it. I have here 2 tickets to take you back in time.
Would I take a journey back in time? Most definitely.
You could change an incident in your past. Would you go back and do it?
I think the Titanic.
I'd probably go back to my teen years.
What about telling the captain, by the way, there's an iceberg coming? Would you do that and interfere with history?
I don't know if I'd interfere with history.
I think that if you actually change something for the better in the moment, it would actually expand something for the positive in the future.
I wouldn't alter, because then you start playing God in there, and that's not right, so.
These were like a one-way ticket, and you couldn't come back to the present. Would you still want to take that trip?
I wouldn't want to go back and not be able to come back to what I know and my children.
I don't believe I'd take the ticket.
I think the present's pretty good.
Living with the past fixed and the future unknown makes us feel secure in time. Change that, and you change everything. So far, we've seen how time, which appears to be so regular, can in fact be quite flexible. We've seen how time can behave in such unpredictable ways. And as we understand more about time, it's even becoming possible to solve perhaps the greatest mystery of them all: whether time is eternal. Over the last 100 years, it's become increasingly clear that our universe, and hence time itself, had a beginning. But that raises another question. If time had a beginning, will it also have an end? Humanity has long pondered the origins of time and the universe. Almost every religion that has ever existed has had its own creation myth. When I was a child, I remember being so confused about how we got here. And that's because I was brought up in between 2 faiths with 2 very different views on creation. On the one hand, there was Christianity. At Sunday school, I learned all the Old Testament stories. Among them, the book of Genesis, describing how the universe came into being in a single moment of divine creation. On the other hand, my parents were both Buddhists. From them, I discovered that Buddhists believe the universe is timeless, without either beginning or end. For some time, I continued to struggle with these 2 seemingly incompatible doctrines. Either the universe had a beginning or it didn't. Either time is eternal or it isn't. It's only in the last 40 years or so that we think we've found the answer. An answer that comes from the furthest reaches of space. The amazing thing about looking up into the night sky is that it's like gazing at a cosmic map of the past. Every planet, every star is like a snapshot taken when their light first left them. The further the star, the more ancient its origins. But for centuries, the limits of the universe were a total mystery, until one man peered further into the heavens than ever before. In doing so, he gave us a better understanding not just of our universe, but of time as well. Perched high in the hills above Los Angeles in Southern California is the Mount Wilson Observatory. In 1919, it saw the arrival of an ambitious new astronomer named Edwin Hubble. Don Nicholson remembers Hubble from regular visits to Mount Wilson as a young boy.
Hubble, certainly as an astronomer, was a very skilled, a very dedicated, very effective astronomer. He was highly respected for his professionalism.
Hubble's arrival more or less coincided with completion of the world's then most powerful telescope, capable of looking further into space and hence further back in time than ever before.
Most astronomers felt that our galaxy was the universe, and for many, that even that the solar system was at the center of that universe.
But on the evening of October 4th, 1923, Edwin Hubble noticed a tiny speck deep within the Andromeda Nebula.
Before that time, there was no telescope in the world, for example, that could resolve individual stars in these spiral nebula. And so there was belief that they were simply gaseous objects in our own galaxy.
But Hubble was able to prove that his speck was indeed a star, and incredibly, that it was more than 1 million light years away, much too far to be part of our own galaxy. In one stroke, Edwin Hubble had destroyed the notion that our Milky Way was the sum total of the universe. And if the universe was much bigger, then it also had to be far, far older. But how much older was still a mystery. Every Thursday, a whole bunch of fans congregate at this drag strip to enjoy the sights, the smells, the sounds of these muscle cars. These unmistakable sounds are created by the same phenomenon that enabled Edwin Hubble to make his second great discovery. Always depend on the direction it's traveling. A car moving towards me sounds high-pitched. but a car moving away from me sounds lower pitched. This shift in pitch, known as the Doppler effect, is due to the fact that at the front of a moving car, sound waves are compressed, while at the back, they're stretched out. And what's true of sound is also true of light. As light moves away from us, its waves too become stretched. By measuring this effect, called the redshift, in one galaxy after another, Edwin Hubble realized that not only were they all incredibly distant, they were all moving away from us. In other words, the universe was expanding. If the universe was expanding, then it had to be expanding from something. From an event whose soundtrack is still with us today. What I'm listening to now are some of the sweetest sounds ever, the sounds of creation. Waves of light from the beginning of time have been stretched so much that we can't really see them anymore. Instead, we can pick some of them up on the radio in the form of static. Although he didn't know it at the time, Hubble's discovery that the universe was expanding led to one of the most important breakthroughs ever made about time, the Big Bang. Once, there was nothing, not even time. But 13.7 billion years ago, it seems that this nothing became everything. When a tiny dot of infinite density spontaneously expanded at a phenomenal rate, giving birth to the universe and everything within it, including time. But if time had a beginning, does that also mean that time will have an end? Just as many cultures have their own creation myth, so most also have their own take on how the universe will end. In the 11th century, the ancient Norse myth of Ragnarok predicted that the universe, and time along with it, would end in a desperate battle between the forces of good and evil. It was believed that this apocalypse would be preceded by something called the Winter of Winters, an epic ice age, during which all the stars would gradually vanish from the sky. How the universe will end continues to preoccupy us over 1,000 years later. In 1988, physicist Saul Perlmutter joined this quest to discover the fate of the cosmos.
It seems like a really philosophical question. Is the universe going to last forever, or is it someday going to come to an end? But in just the last few decades, we finally have both the intellectual tools that Einstein gave us and the practical measurement tools.
Saul believed that the destiny of our universe was linked to the rate at which it was expanding.
Since the 1930s, we've known that the universe is expanding, and everybody's understanding was that it would be slowing down in that expansion because all of the stuff in the universe would gravitationally attract all the other stuff, and so it would slow the expansion down little by little.
This would result in the universe collapsing back in on itself in something called the Big Crunch, bringing time to an abrupt and violent halt.
Are there any decisions coming up? Are there any other ones that we're actually going to have to decide something about?
To discover just when the universe and time would end, Saul and his team began to hunt for extremely rare objects known as supernovae, the aftermath of exploded stars.
There are two things you need to know about a given supernova once you've discovered one. First, its peak brightness. That tells you how far away it is, and hence how far back in time the explosion occurred. The other thing is you want to look at its color through its spectrum. And the more it's been shifted to the red, it's called redshift, the more the universe has stretched since the time of that explosion.
There's only one problem with supernovae, and that's finding them.
These supernovae only explode a few times per millennium in a given galaxy, and they don't give you any advance notice. So we had to invent ways to find them. What we did is design instruments that could bring large numbers of galaxies into a single image. And now, if we look through thousands and thousands of little galaxies on a single image, we could find the one in which their explosions have occurred.
Painstakingly, Saul and his team began to discover one supernova after another.
After several years of the supernova hunting, we had built up a sample of some 42 supernova, and we were finally ready to go back to ask that question that we began the project with: what is the fate of the universe?
But the answer they came up with came as something of a shock.
When we finally graphed the results, we found a very surprising result. Apparently the universe is not slowing down. It was actually speeding up, and that was the big surprise.
In other words, the universe wasn't headed for a big crunch at all. So what will its fate be? Saul's discovery has helped scientists to map out how time and the universe will evolve. An incredible space epic separated into 5 long ages. The first of these was the primordial age, starting with the Big Bang and the birth of time. Lasting only 350,000 years, that's long gone. We're now 13.7 billion years into the second age, and it's only just beginning. We live in something called the Stelliferous Era, an epoch that has brought us not just the stars and the planets, but also every speck of matter in the universe. One day, 100 million years from now, a mere finger click in the life of the universe, this golden age will come to an end. In its place will come the degenerate age, when the last stars burn out and die, when the planets fall from their orbits, and in the darkness of space, matter begins to decay. After a truly unimaginable length of time, only black holes remain. A fourth age that far exceeds all the time that has ever gone before. But even black holes don't last forever. Little by little, their thermal energy will leak away, until ultimately they too disappear. So what does this mean for the future of time? Does the death of our universe mean that time is destined to run out? Or is time really eternal, without end? Even as the last black hole evaporates, a fifth and final age is beginning. The age of the photon. in which time finally fragments into total disorder. When all that remains of our cosmos are invisible, indestructible, low-energy light particles. For Saul Perlmutter, this cold chaos represents the ultimate destiny for time.
This particular picture of the future of the universe, and we don't know if this will be the final answer, would have time lasting forever. There will be no end to the universe in this particular scenario.
So it seems as if both religious traditions that I grew up with are in some sense correct. Time is eternal, as the Buddhists believe. But time also came into being at a precise moment. And that fits well with the story of Genesis. As we look out to the vastness of time that lies ahead, we begin to notice something truly incredible. As we move from one age of the universe to the next, we see that the nature of time itself begins to change. Time evolves. Ultimately, the strange and chaotic behavior that we can only glimpse inside the atom may in general become the nature of time throughout the entire cosmos. And if we could somehow hang around to experience it, we might not even recognize it as time at all. Because just as particles can be in many places at once, so in our quantum cosmos, we might uncover many universes, each one with a time of its own. So this new perspective of time over the whole life of the cosmos makes us look at our time from a new point of view. The time that we feel passing, the time that we know and trust, may be something of an illusion that allows us to make sense of our place in this tiny corner of the cosmos.
Stay with BBC4 to see Ken Russell's TV dramatisation of Lady Chatterley's Lover. Jolie Richardson, Sean Bean and Sean's rather attractive bottom star next.